Myself, Dr. Prashant Kumar Bhattu, Professor, Department of Mechanical Engineering, GIS College of Engineering, Kolani. My subject topics: Advanced Welding Technology, ME 703A. Today is the lecture number 22. Today we'll discuss about the numericals on resistance welding. Numerical problems on resistance welding. Resistance spot welding is a solid state welding process that I already discussed in the previous lecture. So one of the solid state welding is a resistance spot welding. In this welding process, two electrodes are connected in between the lap joint, two plates. Say thickness is T plus T, and the heat is generated by passing current through the electric resistance through the electrode, and the amount of heat produced is dependent upon the resistivity of the material, surface condition, current supplied, and time. So we know that the heat supplied is H is equal to I square RT. H is equal to heat supplied and I is current supplied. R is the resistivity of the material and T is the time. Now, some numericals will be there, objective type, of course. Question number 1, for resistance spot welding of thickness 1.5 millimeter thick steel plate sheet, the current required is of the order of A 10 ampere, B 100 ampere, C 1000 ampere, D is 10,000 ampere. So current required, which one is correct? So we know that 1 to 3 millimeter thickness of plate, current range is required. Current is required is in between 5,000 ampere to 40,000 ampere. Since here T is equal to 1.5 millimeter, it should be more than 5,000 ampere. So answer is D, 10,000 ampere. Normally you will see that minimum 10,000 ampere is required for thickness of T, thickness of 1 millimeter plate. Next, resistance spot welding is performed on two plates of 1.5 millimeter thickness with 6 millimeter dia electrode. This is the electrode, this is electrode. Using 15,000 ampere current for a time duration of 0.25 seconds. Assuming the interface to the resistance to be 0.0001 ohm. The heat generated to form the weld is A 5625 watt second, B 8437 watt second, C 22,500 watt second, and D is 33,750 watt second. Here T is equal to 1.5, electrode dia is 6 millimeter, ampere is 15,000 ampere, time is 0.25, R is equal to 0.0001 ohm, And we know that 1 watt is equal to 1 joule per second. So heat supplied is equal to I square RT in joules. So 15,000 square into 0.0001 into 0.25. This is the time. So total multiply equation will be that 5625 joules. That is equal to watt second. So answer is A. Answer is A. Now, third question, spot welding of two 1 meter thick sheet of steel, density 8,000 kg per millimeter square per meter cube is carried out successfully by passing a certain amount of current for 0.1 second through electrodes. The resulting weld nugget form is 5 millimeter in diameter and 1.5 thickness. If the latent heat of the fusion of steel is 1400 kilojoule per kg, the effective resistance in the welding operation is 2000. The current 200 omega. The current passing through the electrode is approximately A 1480 ampere, B 3300 ampere, C 4060 ampere, D 9040 ampere. Now, here T is equal to 1 millimeter, density is equal to 8,000 kg per meter cube, time T is equal to 0.1 second, electrode dia is 5 millimeter, and Tn, thickness of the nugget is equal to 1.5. Latent heat is equal to L is equal to 1400 kilojoule per kg. So R is equal to 200 into the power 10 to the power minus 6. Dia of electrode that is 5 millimeter. So ml heat is equal to ml means heat is equal to I square RT, where mass is equal to V into rho, V is equal to pi by 4 d square into Tn, so 29.45243 meter cube. So here V into rho into L is equal to I square RT. So 8,000, here the density into 29.4, this is a nugget volume into 10 to the minus 9 into 1400 latent heat into 10 to the minus 3 is equal to I square into 200 into 10 to the power minus 6 into 0.1 is equal to I is equal to, here I is equal to 4060 ampere. 4060 is a C. Your answer is C. These all questions are from the GATE, previous GATE questions. So this is very important question. Number 4. This is which one of the following welding process use non-consumable electrodes? A is gas metal arc welding, B is submerged arc welding, C is gas tungsten arc welding, D is flux-coated arc welding. Here, gas metal arc electrode, non-consumable electrode. We know that in gas tungsten arc welding, tungsten electrode is used. So it is not consumable. So answer is C. Acetyl, next question. Acetylene gas is stored in cylinder in solid form, gaseous form, liquid form, any of this. Acetylene is stored in a cylinder. It is not a dangerous. It is not in solid form, not in gaseous form also. It can be dissolved in acetone in liquid form. Otherwise, it cannot say bottle or in a cylinder. Some charcoal type materials is there where acetone is given, and on that acetone dissolved acetylene. That's why it is called DA, dissolved acetylene. So acetylene stored in liquid form. 6. In TIG arc welding, welding zone is shielded by an atmosphere of helium gas, argon gas, either A or B or none of these. Here also the answer is C. Helium and argon both can be used in TIG welding. So mixed also it can be used. So either A or B or both can be used for TIG welding. Question number 5. There is some process and characteristics applications. So we'll combine all these things, correct the option, answer the correct option. So in P is a friction welding, Q is the gas metal arc welding, R is tungsten inert gas welding, S is electroslag welding. Opposite, one is non-consumable electrode, number 2 is joining thick plate, number 3 is consumable electrode where, number 4 is joining of cylindrical dissimilar materials. So now option is P4, Q3, R1, S2. So P4, dissimilar material. So this friction welding is okay, and Q is equal to Q3, gas metal arc welding. Yes, gas metal consumable electrode, okay. And R is R1, non-consumable electrode. Gas tungsten gas welding is a okay. And this S electroslag welding, S2, joining of thick plate, electroslag welding. B option, P4, Q2, joining of thick metal, gas metal arc welding. R3, consumable electrode wire. S1. Now P2, friction welding joining thick plate. Into Q3, it is not possible. Q3, gas metal arc welding consumable electrode. This is okay, but Q3, R4, R is gas tungsten, R4, joining dissimilar material. Now D is option P2, Q4, R1, S3, electrostatic consumable electrodes. So these are the options. Here you can see the A option is the correct because P4, P is a Friction welding, 4. Joining of cylindrical dissimilar material. Friction welding can be possible. So Q3 gas metal arc welding, 3. Consumable electrode. Gas metal consumable electrode is R1. R1. Yes, tungsten non-consumable electrode is here. S2. Electroslag welding, thick plates. So option A is the correct answer. Now again, calculate the melting efficiency in the case of arc welding of steel with a potential of 20 volt and current of 200 ampere. The travel speed is 5 millimeter per second and the cross-sectional area of the joint is 20 millimeter cube. It required to melt steel may be taken as 10 joule per millimeter cube, and the heat transfer efficiency as 0.85. So in this case, net heat supplied, that is 0.85, the efficiency into 20 volt into amperage. So multiply this, you will get 3400 watt. Volume of base metal melted, that is 520 into 5. 20 is a millimeter cube. Area is 20 into 5. That is, this is 5 millimeter per second. So volume millimeter cube, 100 millimeter cube per second. Heat required for melting is 100 into 10. So 1000 joule per second. So melting efficiency is equal to 1000 by 3400 is equal to 0.2941. So efficiency is a 29.41. So we know that again this formula is very important. So it is given there. Two steel sheets of 1 millimeter thickness are resistance welded in lap joint with a current of 10,000 ampere for 0.1 second. The effective resistance of the joint can be taken as 100 micro ohms. The joint can be considered a cylinder of 5 millimeter dia and 1.5 millimeter height. Density of steel is 0.00786 gram per millimeter cube, and heat required for melting steel to be taken as 10 joule per millimeter cube. This is a heat supplied. Heat supplied 10,000 square, I square, R, this is R, ohms, micro into 10 minus 10 to the power 6 into thickness 0.1. Second, 0.1 second. T is a second. So 1000 joule. Volume of joint is equal to pi by 4 G square into 1.5. So it is 29.452 millimeter cube. So heat required for melting, so 29 point is the volume into 10, 29.452 into 10. That is heat required for melting, this is 10. So this 294.52 joules or 295 joules. Heat loss due to surroundings is 1000 minus 295. This is heat supplied. So heat loss is, this is heat required and this is heat supplied. So heat loss is 1000 minus 295 is equal to 705, that is 70.5%. So in comparison to spot welding, projection welding with a short cycle time would be more efficient. Question number 8. Two steel sheets of 1 millimeter thickness are resistance welded in a projection welding with a current of 30,000 ampere for 0.005 second. The effective resistance of the joint can be taken as 100 microohms. Joint can be considered a cylinder of 5 millimeter dia and 1.5 millimeter height. Density of steel is equal is 0.00786 gram per millimeter cube, and heat required for melting steel to be taken as 10 joule per millimeter cube. Now here heat supplied, I square, that is 30,000 square into R, that's 100 into 10 to the power minus 6 into 0.005. So that is 450 joules. Volume of the joint, pi by 4, height square into 1.5 is equal to 29.452 millimeter cube. Heat required for melting is 29.452 into 10 to 294.52, that is 295 joules. Heat loss due to surrounding is equal to 450 minus 295, that is 155 joules, is equal to 34.4%. Higher efficiency is achieved is because with the time the current is flowing such that the heat losses are minimized. Two metallic sheets, each of 2 millimeter thickness, are welded in a lap joint configuration by resistance spot welding at a welding current of a 10 kilo ampere and welding time of 10 millisecond. A spherical fusion zone extending up to full thickness of each sheet is formed. The effective resistance is 500 microohms. Density is 7,000 kg per millimeter cube. Latent heat is equal to 300 kilojoule per kg. Cp is equal to 800 joules per kilokelvin. Melting temperature is equal to 1793 Kelvin. Ambient temperature is 293 Kelvin. Find the melting efficiency. I is equal to, the current is 10,000 ampere. And T is equal to 10 into 10 to the power minus 3. This time, millisecond. So T is equal to 2 millimeter thickness. Latent heat is equal to 300 into 10 to the power 3 joule per kg. Resistance R is equal to 500 into 10 to the power minus 6. Rho density is equal to 7,000 kg per millimeter cube. Melting point is 1793 Kelvin. Room temperature is 293 Kelvin. Mass is equal to rho into V. I square RT is equal to M into Cp into M, that is mass into rho density into temperature plus latent heat. So 10,000 square into 500 into 10 to the minus 6 into 10 into 10 to the minus 3. Efficiency is equal to 7,000 into 4 by 3 pi. This is 2 into 10 to the minus 3 to the power cube into 800 into 1793, that is melting point, minus 293 plus 300 into 10 to the power 3. That is, so calculating this, so efficiency will come to 70.37. Question number 10. This resistance spot welding of two steel sheet is carried out in a lap joint configuration by using welded current of 3 kilo ampere and welded time of 0.2 second. Molten weld nugget of volume of 20 millimeter cube is obtained. The effective resistance is 20 into 20 micro ohms. Density is equal to 8,000 kg per millimeter cube. Latent heat is equal to 1400 kilojoule per kg. Melting point is 1520 degrees centigrade. Ambient temperature is 20. So one is heat transfer to nugget, we have to find out. Another is heat dissipated to base metal. Now we know current is equal to A ampere is equal to 3000 ampere. T is equal to 0.25 second. Nugget volume is 20 millimeter cube. R is equal to 200 into 10 to the minus 6 omega. E is equal to rho is equal to 800 kg per millimeter cube. Melting point, that is 1520. Room temperature 20. Latent heat is equal to 1400 into 10 to the power 3 joules per kg. This is mass is equal to rho into V. So Q is equal to M into Cp into melting point minus room temperature plus latent heat. So 800 into 20 into 10 to the minus 6, 9 into 500 plus 1520 minus 20 plus 1400 into 10 to the power 3. So total calculating is equal to 344 joule. That is heat. Heat transfer to nugget is, so that is heat transfer to nugget is 344 joule. Now Q ideal is equal to Q ideal means quality heat supplied, that is 12 I square RT. This I square RT is equal to 3000 square into 200 into 10 to the power minus 6 into 0.2 is equal to 360 joules. Heat dissipated to base metal is equal to Q ideal minus Q supplied. Q for the melting of the nugget. So 360 minus 344 is equal to 16 joules. So melting efficiency is equal to 344 by 360 is equal to 95.5%. The objective type question. The major difficulty during welding of aluminum is due to high tendency of oxidation, low melting point, high thermal conductivity, low density. But the major difficulty during welding of aluminum. So here the difficulties, since aluminum is oxidized in air, so oxide of aluminum is a very hard to melt. It's very high temperature is required for melting. So difficult for normal welding process. So here the difficulties is the question. Answer is A, high tendency of oxidation. So if the oxidized aluminum oxidized, the hardness of the material is too high and it cannot be melted quickly. Normally, aluminum will melted at 700 degree, 900, but if it is oxidized, so more than more than 3000 degrees centigrade or more than that is required for melting of that, welding for that. So now another question: during plasma arc welding of aluminum, improves the removal of surface oxides from the base metal is obtained with the typical polarity of question A, DC state polarity, direct current, AC is AC potential, then C is DC reverse polarity, and D is reverse polarity of phase of AC potential. Here the now A, B, C, D. Here the reverse. This is not, but this direct current is not suitable in this aluminum welding. AC potential is suitable. AC potential, no, C. DC reverse is the answer, is this DC reverse. Now another question: two thin sheets are to be welded at a current of 10,000 ampere. Assume effective resistance is to be 150 microohms and the current flow time is 0.4 second. Heat generated during the process is, we have to find out in joules. So given thickness or height of the nugget is 2 into thickness, that is 2 into 1.5 C millimeter. I is equal to, that is current is 10,000 ampere, R is resistance 150 micro ohms, 150 into 10 to the power minus 6 into ohms, T is equal to 0.4 seconds. So we know heat is equal to I square RT. So 10,000 into 10,000 square into 150 into this 10 to the power minus 6 into second is 0.4 is equal to 6,000 joules. Answer. So answer is 6,000 joules. Question number, this is 13. Ascertain aluminum has poor weldability. Reason are aluminum has high thermal conductivity and high affinity to oxygen. So both A are individually true and R is the correct explanation of A. B, both A and R individually true, but R is not the correct explanation of A. C, A is true, but R is false. D, A is false, but R is true. So there, these are the, all are, aluminum has poor weldability is correct also. But connecting to reason is Aluminum has high thermal conductivity. That is also true. High affinity to oxygen. True. So both A and R are individually true, and R is correct explanation of A, right? B, A or R individually true, but R is not correct explanation, right? So answer is A. 14. Ascertain A is equal to is it is generally difficult to weld aluminum parts by normal arc welding process. Reason is hard brittle aluminum oxide film is formed at the welded joints. Both A and R are individual true. R is not correct. Okay. Both A and R are individual true. Same question, so to repeat it. Answer is A. 15. Fabrication of weldability test is used to determine A. Mechanical properties required for satisfactory performance of welded joint. B. Susceptibility of welded joint for cracking. C. Susceptibility for joint design. D. Appropriate machining processes. So fabrication weldability test is used to determine mechanical properties required for satisfactory performance of welded joint. That is correct. So answer is A. Cast iron is difficult to weld because of number one, low ductility. That is true. Two-word fusion, tendency to crack on cooling. So which of these statements are correct? 1, 2, 3. 1 and 2 only. C, 2 and 3 only. 2 is your two-word fusion, tendency to crack. 2 only. And D is 1 and 3 only. So answer is 1, 2, 3. 3 all are equal importance for difficult of cast iron. Cast iron is difficult to weld because of low ductility, pure fusion, and tendency to crack on cooling. 17. The edge of a steel plate cut by oxygen cutting will get hardened when the carbon content is A less than 0.1%, B less than 0.3%, C more than 0.3%, D anywhere between 0.1 to 1%. So answer is more than 0.3 percentage. The answer is C. 18. Consider the following statement in respect to oxyacetylene welding. The joint is not heated to a state of fusion. No pressure is required. Oxygen is stored in steel cylinder at a pressure of 14 MPa. When there is an excess acetylene used, there is a decided change in the appearance of flame. Which of the statements given above is correct or correct? 1, 2, 3. A is 1, 2, 3. B is 2, 3, 4. C is 1, 3, 4. And D is 1, 2, 4. So one is joint is not heated to a fusion. Joint is not heated to a state of fusion. No pressure is. This is correct, but if the joint is heated to a state of fusion is Now, oxygen is stored in cylinder at a pressure of 14 ampere, 14 pascals, megapascals. So, answer is P. 2. No pressure is required used. 2, 3, 4. 19. Consider the following statement in respect of oxyacetylene welding. Joint is not heated to extrusion. No pressure is used. Oxygen stored in cylinder at a pressure of 14 ampere. When there is an excess of acetylene used, there is a deciding change in the appearance of flame. Which of the statement is given above are correct? 1, 2, 3, A, 2, 3, 4, B, C, 1, 3, 4, and D is 1, 2, 4. Answer is D, 2, 3, 4. 2 is no pressure. 3 is oxygen stored in cylinder. And 4 is when there is an excess acetylene use, there is a deciding change in the appearance of flame. Second. 20 question. Consider the following statement. The gas welding, the torch should be held at an angle of 30 degree to 45 degree from the horizontal plane. Gas welding, the size of the torch depends upon the thickness of the metal to be formed. Number 3, drag in gas cutting is the time difference between the heating of the plate and starting the oxygen gas for cutting. Which of the statement is given above are correct? 1, 2, 3 is correct. 2 is drag gas cutting is time difference between the heating plate and starting the oxygen as for cutting. So 1, 2, 3 is not correct. B is 1 and 2. 1 and 2 is a welding gas and torch. Gas welding torch should be angle 45 is correct. Gas welding, the size of the torch depends upon the thickness of the metal to be formed. 2 is okay. C is 2 and 3. Now 1 and 2, 1 and 3. It's not correct, 1 and 3. So answer is 1 and 2. 21. Thick steel plate cut with oxygen normally shows sign of cracking. This tendency for cracking can be minimized by slow speed cutting, cutting in 2 or more stages, preheating the plate using oxyacetylene flame. So answer is preheating the plate. Thick plate for cutting thick steel plate, cut with oxygen normally shows sign in cracking. Tendency of cracking can be minimized. Yes, preheating the plate. Because thickness is high, so preheating is required because of the cutting expanding, or when it's cutting, it is expanded. Certain expansion, so crack may develop. So preheating is required. Thank you.